Hi there, cutie patootie, math angel. Welcome back. Hello, and a very warm welcome if you are new around here. This is Decaf-Math ASMR, and thank you for choosing to check out my channel and for hanging out with us here today. Today we're going to chat more about the Laplace Transform. And we are going to work out the Laplace Transform for two basic functions, namely 1, so constant function, and e to the at, where a is a constant, and so that's our exponential function. And usually those two are the very first two in a Laplace transform table. Sometimes you'll have stuff like t or t squared in there before, in between, but these two are the most basic to solve, and I'll show you why just based on the equation. So of course, as always, before we get started, I wanted to remind you that there's absolutely no pressure around here. There's no comparison, there's no stress, no homework, no tests. It's just time to relax. It's time to slow down. It's time to zone in and out as we wish. It's time to close your eyes and maybe drift off to sleep if you need the rest. It's time to just let the math wash all around you, okay? So if you've been around, you know that I like to jump around a lot anyway, so if you're looking for anything in particular, you might find some stuff in my different playlists, and we'll keep adding to them. But I hope that between all of the videos that you know that the first and foremost goal is to give you a little moment of relaxation, a little moment of peace, stillness, comfort, calm, maybe a tingle or two, a tingle or two if you experience ASMR, and otherwise I hope that this blesses you however you need it in this moment. Okay, so I think I made a little intro video on the Laplace Transform in the past, but I don't really remember what's in it besides the absolute basics. So hopefully this is just the next little step here. Step. You know that math builds on itself, and so we just want to take our time. There's no rush. Don't rush. So here we have the Laplace transform of a function. This function is a function of time, t, and the transform takes this function and moves it into a different world. It moves it so that it's a function of s, and s belongs not in the real world, but in this complex world. And you might see, applications of this. Differential equations in general has a lot of different applications, especially in engineering. And I imagine some people here know a thing or two about that. But we're going to just focus on the math behind all of this today. without getting too abstract. So we take this function of time, and what do we do to transform it? Well, we're going to take an integral. We're going to take this function, and then we're going to multiply it by e to the negative st, and we're going to take this integral with respect to time from 0 to infinity. So this thing is going to give us a function of s, and the reason for that, just kind of intuitively looking at this, is because I'm taking this integral with respect to time, and I have these bounds, 0 and infinity. So basically, I have a t up here as well, but there's this s that I'm going to treat as a constant. So I'm going to work with all the t stuff here, treat s as though it's a constant, and then we're going to deal with these bounds so that the actual t variable goes away and we're left with something to do with s. Now notice that this is basically an infinite sum. If you recall this from calculus, our integral is basically a sum, and so in order for this to actually converge into something, we don't want this to add and take off to positive infinity or negative infinity. Sometimes we need to set certain conditions or intervals for this, so that it actually does indeed converge to something. So that's why if you happen to check out a table, occasionally you'll see this condition, this inequality. So I just wanted to mention that. So basically we handle this in the same way we would from any other calculus class. There's nothing new here as far as that goes. This is an improper integral. We have this infinity here. But you just take your function, multiply by this thing, and evaluate with respect to time, keep s as a constant, and you're going to get a function of s, which looks like this. And so these two are often used interchangeably. We kind of represented the Laplace transform with this capital F here. So, function of s. So why do we care? So if we look at this here, why do we even care at all, right? Like, okay, so someone decided to stick this all into an integral. Great, okay. Well, there are certain properties about this that make it really nice. So it's not just some random integral here. And specifically, what ends up happening is that with the differential equation, like we said, it has just derivatives mixed in, and maybe sometimes it relates it to the original function. Our goal is to find a solution, if possible, to just analytically find a solution, so not just using numerical methods, but actually analytically come up with a solution, if possible. And that is a very messy thing to do unless we have like a particular form, like our Bernoulli situation, which we've talked about here on this channel a little bit. But in general, you might have like a mix of a second derivative and a first derivative, and that's just really messy to look at. And so, you're looking for your solution is a function or a class of functions where the second derivative of that function plus something times the first derivative of that function equals something with that function. And so your solution is basically stuff that satisfies that. Well, that can be complicated, but it turns out that when we switch this over into the S realm, that all of that stuff, the stuff that has to do with the second derivative and whatnot, actually gets converted into an algebraic problem, an algebra problem from, our pre-algebra and algebra work here. So, and that's nice to deal with sometimes, because if you can solve like s squared plus 5s plus 4 equals 0 or something like that, if you can solve that for s, then the algebra world is nice and pretty sometimes, or at least it simplifies our question here. And so sometimes you can transform your differential equation problem into an algebra problem, then solve that algebra problem, get a solution there in that world, and then do an inverse Laplace and transform it back. So it's quite poetic, I think. It's kind of like looking at something that is just overwhelming, lots and lots of pieces to it, don't know where to start. And then suddenly there's this aha moment where we can just switch our perspective a little bit. So our Laplace comes to the rescue and says, wait a minute, we don't have to even look at it in this world. Let's just take a different perspective, make this something nice and pretty. We'll play around with some algebra, and then we'll just send you back. It's kind of like a little Laplace fairy godmother or something that just comes and saves the day. It just transforms the question altogether into something else. So it's our Laplace fairy godmother or something. I always seem to outdork myself, but you already knew that. We've already crossed that bridge a long time ago. Probably when I started this channel, to be honest. But yeah, it really is that cool. It transforms it into an algebra thing, and why does it and how does it do that? So basically, just intuition wise here, so if we have a bunch of S stuff here, one of the properties, and we're going to actually probably derive this at some point, but basically, first thing is the Laplace transform, because it is this integral, is a linear thing, meaning that if I have the Laplace transform of let's say 1, then the Laplace transform of 5 times 1, or constant times 1, is the same thing as that constant times the Laplace of 1. So you can pull out constants like you would with the derivative, right? So that's not always the case, but this happens to be true. And if you have the Laplace of the sum of two things, you can take the Laplace transform of each of them and add. So because of that, you can take the Laplace transform of an entire, the second derivative plus the first plus whatever in your equation, and end up taking the Laplace transform of each term, the stuff that's separated by pluses or minuses. So you take the Laplace of each term, and then you can use this. And it turns out that when you take the first derivative, the Laplace of a first derivative of a function, it turns out that in the S world, you basically have an actual S. And when you take the second derivative, you have an S squared term. There's more to it. You'll have an S squared and an S and a constant term. But the idea is that as you get higher and higher in your derivatives, you have higher and higher degrees in your S parts. So you'll have like an S squared thing here. So you could start to see that you're going to have powers of S, and that kind of starts getting us into this algebra stuff. So, in other words, as you take an extra derivative, you're multiplying by a power or another factor of S. And then we have to deal with the initial boundaries and stuff like that. So we'll work this out, but that just happens to be a property of this. And so this e to the negative st part is actually very special. So before we do all that, like I said, today I want to calculate the Laplace of 1 and e to the at here. So we're not going to get quite into that deriving of the s and s squared stuff, but we will do that the next time we come back around. I think this stuff is cool. But today I want to start with these two basic ones, because if you've taken calculus, or if you're taking calculus now, you'll know that when you first learn about the derivative, you often start with a basic limit definition, right? Like the limit as h approaches 0, this thing, the f of x plus h minus f of x, right? And that's just the strict definition of it. And then you learn where it comes from, what does the derivative mean, how that's the slope of the tangent line, and at different x's and that kind of thing. But when you're first introduced it, you just start with the core definition. Then you may play around with it a little bit more and try out different functions, maybe a constant function, maybe a linear one, and do that by hand, do that limit by hand. Speaking of, we should come back and do some of those and play around with them. And so then you realize, okay, this is a pattern. We can put these all into a derivative table, just basic ones that we can use often but don't have to keep recalculating over and over. And then we can make other functions by combining the basic ones, like multiplying them and using the product rule, or dividing with the quotient rule, or doing some compositions so we can use the chain rule. But basically, if we can break down our derivative to one of these basic ones, we can just refer to our table or just memorize them if we use them often. But that's the idea, right? You don't have to keep going back to this limit definition over and over and over again. That's how we have all these little rules. And it's kind of the same thing here. I feel like here's our strict definition. You can just always plug into this. But we do have a Laplace transform table that we can refer to. But I think it's always good to be able to calculate this and sort of confirm the first few entries of a table, just to make sure that we understand where this comes from and how to actually work with it. If you can prove it once, then you can use it. That's what I like to remind myself. And sometimes that's a pain, but in this case I think it's quite fun. So let's do 1 first, because that is like the most, like that's the root constant function. So let's see what we can get. So like I said, our goal here is going to be to start making a table where we have an f of t here, and some tables might say y of t, and then on this side we'll have f of s, which is our Laplace transform of said f of t. So we're going to do 1, and then we want this thingy, and then we want e to the at here. And if you happen to be just zoning in and out, or just kind of tuning in and out, this is not a subliminal message to go EAT. Anyway, we're just going to do some calculations now, and all we're going to do is plug in that 1 here. So, and I know what we're expecting, but I haven't actually worked this out. So I'm hoping that we actually end up getting something useful, or else I'm not going to have much of a video now, am I? So, the Laplace transform of 1, meaning constant function f of t is 1, is, and so we're just going to plug into this. So we have 1 times e to the negative st dt. Okay, so this is why this is so nice to work with, because the 1 goes away. 1 times anything is itself. So we can just do this e to the negative st dt. So now this is more of a calculus question than anything else. We're just going to evaluate this integral, and just as a little heads up, the Laplace of e to the at kind of fits into this nice pattern here as well, because if we put e to the at times e to the negative st, we can use a basic exponent rule to combine that into e to the stuff as well. So there's a reason that these two are chosen first. So again, we can use whatever calculus methods we know, use substitution, integration by parts. So these first two don't involve integration by parts, whereas the ones, down the table often do. So we're going to just deal with this, and here you can do this however you want. I'm going to start by just giving you this integral first, because there's this pattern here. I think it's easier to see going the other direction. So we treat s as a constant here, right? We're integrating with respect to time. And the nice thing about exponential, so e to the stuff, the derivative of e to the stuff, or rather e to the x with respect to x is e to the x. The derivative of e to the t with respect to t is e to the t. So it stays the same as you take derivatives. And we draw on that a lot here in Diff Eq. But basically, you might think, okay, if I take the derivative of this thing, I'm hoping to get e to the negative st back. That's what it means to take this integral. And we have bounds, so we don't need a plus c. But you might think, okay, well, if the derivative of e to the t is e to the t, then the derivative of e to this negative st must be e to the negative st. And it is, kind of. So you keep this e to the negative st when you take the derivative, but you also need to multiply by the derivative of the top thing, because it's not e to the t here, it's e to the stuff. So you treat it as though that stuff is a t, so you keep this e to the negative st, but then you have to also chain on the derivative of this, which would be negative s, because the derivative of t is 1. So you have a negative s e to the negative st, because of the chain rule. And then because there's a negative s on the side, it cancels out with this negative s down here. That's why we're dividing by this negative s. So then the negative s's cancel, and you're left with e to the negative st when you take the derivative, which is exactly what we wanted here. So that might just seem random, because that's like an after the fact, like, oh, well, you integrated and then told me that the derivative of that integral is this thing. If we were moving in the forward direction, you could, well, as you work through more stuff like this pattern becomes it comes up a lot, so it becomes kind of repetitive and you kind of can jump right into it. But for the first time, you can also just do a little u substitution. So you can let u equal negative st if it helps you see it this way. So this way you translate this entire thing from a t expression to a u expression. This is our u sub, and so this would lead to du being negative s dt. So then dt is du. So I ran out of ink here, but it's du negative s. Okay, so you can translate this whole thing, including the bounds. So if you do this, you have to make sure your lower and upper bounds work for t, and then translate it all in terms of u. So you'll want a du, and if you work that out, you'll end up getting the same answer. You might skip this step in between, but you'll get the same answer here for our Laplace transform. But I'm going to leave it in this form because there's something I want to say about it. So just as a little heads up though, if you don't recognize this part, you need an extra step, that's totally okay. Just throw in a little bit of a use up here and it's no big deal. Okay, so what I was going to say here is earlier I mentioned needing to potentially set certain intervals in order for this sum to actually converge, right? In order for this integral to converge. And this is exactly that case. I need to set s greater than 0 because if t is going from 0 to infinity, so that's positive, if s were less than 0, then we have a negative times positive, which would be positive, and t is going off to positive infinity, so this is getting exponentially large. It takes off to positive infinity, and that's a problem because that sum is never going to converge to anything. If s equals 0, then we have 0, and this negative doesn't matter, 0 times whatever t is going to be 0, so e to the 0 is 1, and that integral is going to be t, and since t goes from 0 to infinity, that also takes off, right? It's going to go off to positive infinity, also a problem. So all that is left is for s to be greater than 0, and also we can't divide by 0 here, but s is greater than 0 because then we have negative times positive number times something that goes off to positive infinity, and we have e to the something negative, something that goes towards infinity. And we'll write this more properly here in a second. But that's nice because then with the negative exponent, we can bring that down to the denominator of a fraction. And that's just how negative exponents work. Like 5 to the power of negative 2 is 1 over 5 squared. And this is nice because as t goes to positive infinity, this e to the thing, assuming that s is greater than 0, now goes off to infinity, which normally is a problem because that won't converge. But if it's on the bottom of a fraction, if it's in the denominator, then this thing actually converges and it goes to 0. It's kind of like if you have a pizza and you're sharing it with an infinite number of friends, so you keep slicing it up to share with more and more people, eventually, basically, your slice will be non-existent. So, moral of the story, share your pizza, but not with too many people. So, that's the general idea. We're going to write out to this limit here in a second, but that's why we want s to be greater than 0. At least a general idea for why. So now we have our bounds from 0 to infinity, and we kind of deal with each bound like we normally would. We do upper and then minus the lower, but we want to kind of avoid thinking of infinity as a number, right? We're not just going to say e to the negative s times infinity over negative s. If you were to just try and calculate this, you kind of can think about it that way. Don't tell anybody and don't write e to the negative s infinity for sure. But infinity is not a number, but you can kind of think about what happens when infinity, like when this t goes larger and larger and larger. So you can go ahead and just note what we did here, that it goes off to 0, but we're it converges to 0 for this first part, but let's just write this out. So we can instead just put a little placeholder variable, maybe like an n or something, and take the limit as n approaches infinity. So this is more proper. But from your pal Decaf to you can basically think of it as t going off to infinity. And then for 0, so we do the top part and then minus the bottom. 0, I'm plugging into t, right? So 0 times this negative s is going to be 0, e to the 0 over negative s. So now we just do each part. And so now it's fine, we're not plugging in infinity, but as n approaches infinity, as this number gets bigger and bigger and bigger, we said this negative exponent brings it down to 1 over e to the something very big, which is going to be 1 over something very big, and then over this negative s. And since s is greater than 0, this thing will actually go to 0, like we said. And this part is just so satisfying, so we're going to mark this off. This whole thing goes to 0. So we have 0 minus, and then e to the 0 is 1, and then we have a negative s. And this negative become positive. You can think of this as 0 plus 1 over s, or justify it how you wish, but you can do a negative 1 over negative s, but it ends up being 1 over s. 1 over s. So the Laplace transform of 1 is 1 over s, given that s is greater than 0. So we need that condition in order for this thing to actually converge. Okay, so I hope that makes sense. You can do this U substitution for sure if you want this intermediate step, but we're about to do the transform of e to the at, and you'll notice this exact same pattern again. So just even 2 for 2 examples, you can kind of start to see this e to the stuff pattern. So of course with more practice you'll definitely kind of notice this to just divide by this coefficient. So let's work out this one, and it's actually very similar, basically the same, but just one extra little step. So I'm going to do e to the at here times e to the negative st dt. So we put this e to the at thing into the equation again. And now we can use our exponent rule. We have the same base and raised to the stuff, and we're multiplying, so we just go ahead and add the exponents. So we have e to the at plus negative st, but that's the same as at minus st dt, which is great. And now I'm just going to factor out this t. So I have e to the a minus st dt. And so this looks very similar to this e to the negative st stuff, but now we just have other stuff in front. But the reasoning is exactly the same. In order for this thingy to converge, I need for a minus s to be negative. So a minus s less than 0, which if we solve that, we just need for s to be bigger than a, which makes sense because if s is bigger than a, then when we do a minus s, that's going to be a negative number. For the same exact reason as we did before, we want this to go down in the denominator of a fraction so that when t goes off to positive infinity, this thingy actually converges. And we also don't want this to be equal because this would be 0 and we'd be taking the integral of 1, and that would be t, and t goes off, so that still doesn't converge. So we just need s greater than a. And so again, we can do a u sub let u equal a minus s times t, but we can also just go ahead and do the same a minus st pattern, but when we take the derivative of that, we have a coefficient of a minus s due to the chain rule. So we'll divide by an a minus s to get rid of that, to get our e to the a minus st back. So we have our 0 to infinity, and at this point here, since we already worked it out here, the limit part, the limit as n approaches infinity, I suppose I'll write it down again. I guess I'll use the back of this another time for scratch paper. I just want to be able to reference this if we need to. But we would have the limit as n approaches infinity of e to the a minus s n over a minus s, and then minus the 0 part, which is e to the 0 over a minus s. So that's our upper and lower bound part. And again, in my opinion, most satisfying part is that this will go to 0 if s is greater than a, because this part's going to be negative with our negative exponent as n goes to something infinitely large. This thingy goes to negative infinity, which is 1 over e to the something very large, which goes to 0. And this a minus s part is kind of inconsequential. Is that the word, inconsequential? It's just not important to this because we're taking the limit as n approaches infinity. So this isn't going to make a difference. And so all we have is here. So I love when things look complicated, but it's actually like whoop, 0. So then what's left here is a negative e to the 0 is 1 over a minus s. And you can kind of mess with this how you want. You can kind of make this negative, like 1 over negative 1, and then distribute out this negative 1. Justify it however you want, but you can get 1 over s minus a. It just flip-flops the order of this. So we have 1 over s minus a as our Laplace transform. So let's write that in. The Laplace transform of e to the at is 1 over s minus a as long as s is greater than a. So as you notice here, as you might notice, when we have this e to the at, so like e to the 3t for instance, the Laplace transform would be 1 over s minus 3. So where there's this exponent here, this coefficient of the t thing, that where s equals a, this thing blows up. It blows up because we divide by 0, so we break the math, right? So we'd have 1 over 0, which would be a problem. So there's this thing called a pole at s equals a. So in our f of t world, if we have e to the at, in our complex s world, we have a pole. And if you look at this a little closer, this is actually a special case of this one, right? Because if a happens to be 0, so if a equals 0, then you have e to the 0, which is 1. And if a is 0 here, you have 1 over s minus 0 is 1 over s. So this is kind of a little special case of this. Okay, so I hope that that's cool. So I know right now it might just seem kind of like, well, who cares what, like, okay, so in that, well, I don't know if who cares, I think it's cool, but you're looking at 2 different worlds and you're looking at things that are equivalent here, but it doesn't really mean anything to us as far as solving certain equations, right? But as you can imagine, like we said, because the Laplace transform is linear and we can do the Laplace transform of each little piece, whenever you see a constant, so let's say you have a minus 7 or something, then when you translate that piece into the complex s world, you would have negative 7 over s. because that's negative 7 times 1, and 1 goes to 1 over s, so negative 7 would go to negative 7 over s because this is linear. And if you have like an e to the 5t or something, then in the s world you'd have 1 over s minus 5. And so this starts to give us something like at least a first look into translating stuff into an s world where we can then do some algebra. But in order to actually get to that algebra piece, we definitely do have to work out the Laplace of a first derivative or second and how that relates to the original function and stuff like that. So we're going to get into that. That's going to involve probably an integration by parts, because I see if I have a derivative here and this, then we'll probably need an integration by parts to show that. So I guess I'll leave that for another time, but it really comes down to this e to the negative st bit. As you know, if you've been learning Diff Eq, or if you have, this exponential thing is very, very handy. So I hope that you've enjoyed this. I'm glad that we got to do something at least. These two were exactly what I expected to get, so I'm glad we could actually kind of confirm it. If you are asleep right now, I'm wishing you sweet, sweet mathy dreams. If you are going to continue on with the rest of your day, I hope that it's a good one. I hope that you have a wonderful, wonderful week, and I will see you around for more math very, very soon. Please take good care. Take good care. Sending you much love. Bye-bye. Bye-bye. Bye-bye.